Okay, so here we go. We just spent a lot of time talking about this formula, okay? And we're going to assume the point of interest here is fixed, is a fixed axis, not moving, with respect to the inertial frame. And let me simply say, this is an exercise in stating the obvious. Angular momentum is conserved. And what that is stated analytically looks like this. Is a constant. So, and we told you last time as well that the angular momentum is the moment of inertia times the angular velocity. So if we're talking about an object that's rotating about a fixed axis, and let's talk about two different states, okay? State number one, it has an angular momentum, and then in a second, it somehow gets to a second state with no external torques applied, then you know that these two are equal. From which it follows that that's the case. That's I2, omega 1. Okay. Let me just say the iconic example of this. You guys like sports? Yeah. Ever watch the Olympics? Yeah. This actually, it didn't come from the Olympics. This came from Johnson Arena, okay? So watch this. I think you know where we're going with this. This is one of your fellow undergraduates. Okay, good job. Yeah, I'm sorry I can't remember the gentleman's name, but that was a very artfully done spin, not a simple matter. Noam, why is this relevant? What am I talking about up here? What does that represent?
When he brings his arms closer to him, he's reducing his I, so W has to go up.
Exactly. What we talked about last time was that in general, this is some kind, the moment of inertia calculation is some kind of guy like that, all righty? That is, again, in the case of a figure skater, it's a little more involved, all right? I can't go through all the M sub i's and R sub i's, but what you can say is that in general, if there's a figure skater with their arms out that's spinning, about a Noam, is that person's moment of inertia larger or smaller than when they pull their arms in?
Larger when your arms are out.
Yeah, larger when your arms are out, larger when your arms are out, larger when your arms are out, smaller when your arms are in. So the angular velocity after pulling your arms in is larger. All righty? Everybody got it? That is that. Okay. I am going to skip. I had an example where, let me just put it this way, kind of a conceptual example. I'm going to forego this. What I had was two masses like this spinning at an angular velocity omega 1 at a radius r1, okay? And then sometime later, they moved into a smaller radius position analogous to the figure skater. And you basically can demonstrate to yourself that that's the case. You go, Noam, here's a curveball, no pun intended. If angular momentum is conserved, well, first off, why is it conserved? There's no external torque. Okay, how about this? Curveball. Was kinetic energy conserved?
Yes. No.
Okay. Okay, that's a 0.5. I think that's a. No, you should go to Washington. You're the one that needs to go to. Okay, perfect. Anyway, in the interest of time, what was I asking? Anyway, the answer is no. All right, the answer is no. The kinetic energy is not, I don't know what the symbol is not conserved. All right, work it out. Trust me, that's the case, and you'll need that on the problem set. Now here's the last one. I've been saving this because there's a real I have a demonstration here. This is a little different one here. Imagine you have two rigid bodies, one with a moment of inertia I1 spinning at omega 1 and another of different I2 spinning at a different angular velocity. Okay, and then all of a sudden somebody goes, claps them together. Okay, physical analog would be, a DJ, turntable, conventional vinyls, drops one circular disc onto the other. Question on the floor? About it, Noam? How would you approach it?
I'm assuming they're sticking, so I would say.
Oh yeah, eventually, yeah, exactly. They slide initially and then they finally stick. And
so their final angular velocity has to be equal. So you.
Yeah, and that's what we're talking about. When they're done, they spin as one.
You do the individual momentums have to equal the final momentum.
Exactly. That's exactly right. And analytically, this looks like this. I'm kind of dressing it up here a little bit. It looks like that. Basically, it says what this is the total angular momentum before the fact. Okay? Before the fact, angular momentum 1, angular momentum 2. After the fact, they spin as one with I1 plus I2 being the moment of inertia, and that's the okay? Makes sense? Now, I actually have a demonstration for you. This is sparing no expense. This is my office chair. Okay, I think you can appreciate it as a lifetime academic. I have strong feelings about this chair. You get rather attached to them after a while. This one swivels, and today this thing is going to serve as a rotation table, a frictionless table. It's not that frictionless, but it's okay. All righty? I want you to tell me, those of you can see me, Alex, you can see me, you're the court announcer. I want you to tell me what's going to happen, what happens when I do this. What's moving where? Careful now. What I won't do to make a point, I got to tell you. Anyway, Alex?
It looks like you're moving your body with a
Oh, okay, that's good. You saw something different. James, was that what you would have said? Or did you hear what he said? He said the chair moved one way and you moved the other.
Well, half of you is moving one way and half the other.
That's thing. Nicely put, James. Very delicate. James said half of me was moving one direction and the other half the other. And that was precisely what I was looking for. As far as the way it felt to me, and with and Alex, you're right too, to the extent this is a crummy, frictionless rotation table, that's, you're right. But if it were a better rotation table, James's correctness would be even clearer, okay? Because you would be able to see my upper body spinning one direction, my lower extremities rotating in the other. James, why are they rotating in different directions? Well, okay, but James says because there's no external torques. Good answer. Okay, what I was looking for, when there's no external torques, all that says is whatever the angular momentum was, it will stay that way. So now, you want to take another shot at that? What was the angular momentum of the system before I started? Yeah, it was 0. I was just sitting in the chair. Nothing was moving. And then, it's still 0, because even though the upper body is rotating in one direction, the lower body is rotating in the opposite direction. There's a minus sign in there. These things are going like this. Okay? Very good. Questions? Comments? Oh, yeah, hang on. Kimmel. I'm sorry, Professor Vandenberg. Yeah.
That equation also works when the 0 is G and it doesn't actually have to be a fixed axis.
Point taken. Okay, everybody hear that? Professor Vandenberg quite correctly pointed out that the point be a fixed axis of rotation is not a requirement here. It can just as easily be the center of mass. In particular, it can be the center of mass and there's no change to the discussion. Clear enough? Okay, question?
With the conundrum, why then turn over when it's falling and there's no external force?
Ooh, very good. Excellent question. Curveball for next time. I don't think there's any reward for this, but Professor Vandenberg's thrown out the question, why is it cats land on their feet if they can't access any external torques? I'll show you a video next time. Hold a cat upside, I didn't do it. Hold a cat upside down, turn them loose, they land on their feet. Okay? Next time. See ya.